Welcome everyone. I'm excited to start our journey into the fascinating world of science. Today, we're going to explore the basics of understanding electricity. We'll look at how electricity works, why it's so important, and how it impacts our daily lives. So, let's get started and uncover the secrets behind this powerful force. Today, let's explore what electricity is by looking at its two main types. First, we have static electricity, which is what happens when charges stay still, like when a balloon sticks to your hair after you rub it on your clothes. It's all about those stationary charges. Then, there's current electricity, which involves charges flowing continuously, like the battery in your flashlight powering the bulb. The key idea here is that electricity is essentially the flow of electrons, which are negatively charged particles. These electrons move through conductors, like wires, allowing us to power everything from lights to computers. Understanding these two types helps us see how electricity works in different situations, whether it's static shocks or the electricity running through your devices. Overall, electricity is all about the movement of tiny particles that make many of our daily technologies possible. Let's start by understanding electrons. They are tiny particles that carry electrical charge. When we talk about moving electrons, we're often referring to the flow from the negative terminal to the positive terminal. Think of it like water flowing through a pipe, where the pressure pushes the water along. In electrical terms, this pressure is what we call voltage, measured in volts or V. Voltage is essentially the force that pushes electrons through a circuit. The higher the voltage, the stronger the push. Now, as electrons move, they create a flow called current, which we measure in amperes, or you can think of current as how much water is flowing through the pipe at any given time. But there's also resistance, which is like a partial blockage inside the pipe. Resistance opposes the flow of electrons, making it harder for them to move. We measure resistance in ohms or omega. The more resistance there is, the less current flows for a given voltage. So, to tie everything together, voltage pushes electrons along, kind of like water pressure, and current is the flow of electrons, or how much electricity is moving. Resistance opposes that flow, just like a narrowing pipe slows down water. Understanding these key concepts helps us see how electrical circuits operate and how to control the flow of electricity effectively. Let's take a closer look at some of the best conductors used in various applications. Copper is often considered the top choice for wires because of its excellent ability to conduct electricity efficiently. It's widely used in many electrical systems around us. Gold, on the other hand, is used in high-end electronics because it resists corrosion and provides reliable conductivity, especially in delicate or high-performance devices. Steel, while not as conductive as copper or gold, is used in power lines because of its strength and durability, often combined with other materials. Aluminum is another common conductor in power lines because it's lightweight and cost-effective, making it suitable for long-distance transmission. And then there's silver, which actually conducts electricity even better than copper, though it's more expensive, so it's used in specialized applications. All of these materials are excellent examples of conductors, substances that allow electric charges, or electrons, to flow easily through them. Recognizing these differences helps us understand why certain materials are chosen for specific electrical and electronic uses. Let's take a closer look at insulators and their important role. These materials are used in many everyday items, such as wire coatings and gloves, to prevent electric shocks. You'll also find them in outlet casings and bottle materials, where safety is crucial. High-voltage insulators are essential in power lines to keep electricity contained and prevent leaks. They are also used in fuse boxes and spark plugs, ensuring safe operation of electrical systems. The key point to remember is that insulators are materials that do not conduct electricity when dry. Some common examples include rubber, plastic, glass, ceramic, and dry wood. These materials effectively block the flow of electric current, making them vital for protecting us and maintaining safe electrical environments. So, whenever you're working with or designing electrical systems, choosing the right insulator is critical to ensure safety and proper function. Now, let's take a closer look at how electric circuits work by exploring two main types: closed circuit and open circuit. When we talk about a closed circuit, we're referring to a complete path through which electrical current can flow. Think of it like a circle that is intact and unbroken. This allows the electricity to move from the power source, through the various components, and back again. This is essential for devices to operate because the current needs a continuous path to flow smoothly. On the other hand, an open circuit is like a break or gap in that pathway. When there's a gap, the circuit isn't complete and electricity can't flow. This is often what happens when a switch is turned off or if there's a break in the wiring. Without a closed loop, the current stops flowing and the device won't work. Understanding these two concepts is key because they highlight the importance of a complete circuit for electrical devices to function properly. Whether we're designing circuits or troubleshooting, recognizing whether a circuit is open or closed helps us identify what needs fixing or what's working as it should. It all ties back to the overall theme of understanding how electricity moves and powers our everyday devices. Let's take a closer look at some of the key components of an electric circuit. First, we have the power source, which is essentially the battery or generator that provides the electrical energy needed to make the circuit work. Without a power source, there's no flow of electricity. Next, we have conductors. These are usually wires made of materials like copper or aluminum that allow the electrical current to travel smoothly through the circuit. Think of conductors as the roads that guide the electricity from the power source to where it's needed. Then we have switches. Switches are like traffic controllers. They turn the flow of electricity on or off. When you flip a switch, you're opening or closing the circuit, which controls whether electricity flows to the load. Finally, the load is what uses the electrical energy, like a light bulb or a motor. It's the component that performs a task or produces a result based on the electrical power it receives. Putting it all together, these elements, power source, conductors, switch, and load, work in harmony to make electric circuits function effectively. Understanding how each part contributes helps us see the bigger picture of how electricity powers our everyday devices. Let's talk about resistance, which we denote as R. Resistance is essentially the opposition to the flow of electrons. We measure this using an ohm meter. For example, a resistor is a component that limits the current flowing through a circuit, protecting parts like an LED from too much current. Now, moving on to current, represented by I. Current is the flow rate of electrons passing through a point in the circuit, and we measure it with an ammeter. For instance, an LED typically uses about 20 milliamps, or 0.02 amperes, of current to operate properly. Next, voltage, represented by V, is often called electrical pressure. You can think of it as the push that drives electrons through the circuit, and we measure it with a voltmeter. For example, a typical AA battery provides around 1.5 volts, while a car battery supplies about 12 volts. Understanding how resistance, current, and voltage relate helps us grasp how electricity flows in a circuit. By measuring these, we can better control and troubleshoot electronic devices and ensure they operate safely and efficiently. All right, let's look at a real-world example to understand Ohm's law better. Imagine you have a dimmer switch on a lamp. When you turn the dimmer, it increases the resistance in the circuit. Because resistance goes up, less current flows through the bulb, and as a result, the bulb dims. This simple example shows how resistance affects current and brightness. Now, what's the key takeaway here? It's the fundamental relationship expressed by the formula voltage equals current times resistance, or V equals I times R. This tells us that for a given voltage, if resistance increases, the current must decrease. Conversely, if resistance drops, the current can increase. So, in practical terms, when resistance is higher, less current flows, and that's why the bulb dims in our example. This is the core idea behind Ohm's law, and understanding it helps us see how voltage, current, and resistance are all interconnected in any electrical circuit. Remember, this relationship is fundamental because it applies to so many scenarios, from household wiring to complex electronic devices. It's the foundation for designing and troubleshooting electrical systems, so keep this in mind as we move forward. Now, let's take a closer look at the differences between series and parallel circuits. On this slide, we see two types, the series circuit and the parallel circuit. In a series circuit, the components are connected end-to-end in a single path for the current to flow. If one component fails or is disconnected, the entire circuit is broken, and current stops flowing. This means that the voltage divides among the components, and the current stays the same throughout the circuit. On the other hand, in a parallel circuit, the components are connected across the same voltage source, creating multiple paths for the current. If one component fails, the others can still operate because the current has alternative routes. Importantly, in parallel circuits, the voltage across each component is the same, but the current can vary depending on each branch's resistance. Understanding these differences helps us see how the circuits behave under different conditions. Series circuits are simple but less reliable, while parallel circuits offer more flexibility and safety. Recognizing these distinctions is key as we explore how circuits are designed for various applications in electronics. Now, let's look at how circuits are used in everyday life. For example, in home wiring, we typically use parallel circuits. This allows multiple appliances to operate independently, so if one device is turned off or fails, the others continue to work without interruption. You might also be familiar with older Christmas lights, which often used bulbs in series. In this setup, each bulb works independently, but there's a catch. If one bulb burns out, it breaks the circuit and all the lights go out. This highlights the key difference between series and parallel circuits. In a parallel circuit, there are multiple paths for the current to flow. This means the current can split and go through different branches, so each device has its own direct path to the power source. In contrast, a series circuit has a single path for current. The current flows through each component one after the other, so if one part fails, the whole circuit stops working. When comparing these, the main takeaway is that parallel circuits provide more reliability and flexibility, especially in household wiring, while series circuits are simpler but less resilient. Understanding these differences helps us see why we choose certain types of circuits for specific applications and how they connect to our overall electrical system. Let's take a closer look at some special electrical components that play crucial roles in our everyday devices, starting with the inductor, which stores energy magnetically. You'll find these in streetlights and power supplies, helping to regulate current flow smoothly. Next is the LDR, or light-dependent resistor, which changes its resistance based on light levels. This makes it perfect for automatic lighting or outdoor sensors. Then we have the thermistor, a component whose resistance varies with temperature, often used in fire alarms or temperature sensors. Lastly, the diode allows current to flow in only one direction, which is essential for converting AC to DC in power supplies and protecting circuits. These components are fundamental to many systems, highlighting how specialized electrical parts enable the technology we rely on daily. Now, let's take a look at how electricity can be generated from different sources. On one side, we have non-renewable sources, which include fossil fuels like coal and gas, and nuclear power, which relies on uranium fission to produce heat. That heat then creates steam, which drives turbines to generate electricity. These sources are limited and can cause environmental concerns. On the other side, we have renewable sources, which are more sustainable over the long term. For example, solar panels convert sunlight directly into electricity, making use of the abundant energy from the sun. Wind turbines harness the kinetic energy of the wind, transforming it into electrical energy. Understanding these different methods highlights the importance of transitioning towards renewable energy, especially as we aim to create a more sustainable future. It's crucial to recognize how each source contributes to our electricity supply and the role they play in reducing environmental impact.